So you remember Bertrand and Cournot from what first year did you do it? That's a long time ago. So what we're going to do is we're going to go over Bertrand and Cournot again, and you know, you're going to see some surprising properties about Bertrand and Cournot. So you know, if I said which has high profits, Bertrand or Cournot, which would you say? Well, in fact, it can be Bertrand, and that was supposed to be the surprise. You're all supposed to say Cournot, because in what you've seen before, Cournot normally has higher profits. Bertrand is the perfect competition thing, right? The price is getting pushed down to zero. I just want to turn off the display. Trying to save my battery though, yeah. Right, sorry about the late start to this lecture. It's bad luck with the camera. Okay, things going, you can see. So we're going to start by just revising some game theory. Then we're going to go on to show you Bertrand competition again, just to remind you what it's like, and then we'll go on to Cournot competition at the end. Okay, you've seen these things before, but they'll be the basis for a lot of what we're doing later, so it's important to remind yourself of what these things are, okay? Okay, so I'm going to show you a few games and just remind you of these key concepts in game theory, which I'm sure you've heard of. So, you know, you've heard of Nash equilibria. Yeah, so you should have done all this work. Okay, so we're going to see what the elements of a game are, what it means for a strategy to be dominant or dominated, and then we're going to go on to look at what a Nash equilibrium is. Okay, and if you need some more, if you need a reminder of this stuff, it's all in Oshai 2.1. I'm trying to save the battery on my laptop. This is the last of them. Okay, I give up. Okay, right. Let's go to a prisoner's dilemma. Okay, so you remember this game, right? We're two prisoners. They're in separate cells. Okay, and they're both being questioned about the same crime. Each of them is going to be offered a deal. Okay. If they give evidence that the other was the one who committed the crime, okay, then they're going to walk free, at least as long as the other one doesn't give evidence against them, okay? And if they do give evidence against the other person's going to jail for 3 years, okay? So if you screw over the guy in the other cell, he's going to suffer for a long time. But if you both offer evidence against each other, okay, then the police know you're both involved in the crime, okay, and you're both going to go to jail for 2 years. But if you both keep quiet, no one says anything, police can't really pin anything on you, they just you know, accuse you of trespassing or something, some very minor crime rather than robbery, okay, and so you both end up going to jail just for 1 year. Okay, and we normally represent these games in a block like this. You've seen these things before, right? Okay, so the rows give the actions of the person over here. Okay, so prisoner A can either cooperate and stay quiet, or defect and give evidence against the other person. Okay, person B can either cooperate or defect. Okay, so if person A cooperates and person B cooperates, we get this cell here, okay? And that says this person's going to prison for 2 years, this person's going. Sorry, this person's getting a utility of 2. So I've transformed it into utility, okay? So utility here is 3 minus the number of years in prison. So, yeah, so if both people cooperate, if both people stay quiet, you go to prison for 1 year. So let's say you get a utility of 2. Sorry, that's what I've done now. If person A stays quiet, but the other person gives evidence against him, then person A gets a utility of 0. He's going to prison for 3 years. Person B gets a utility of 3 because he's not going to prison at all. He's walking free. Okay? So this is just the standard way we represent the utilities in one of these games. So, you know, when you're doing game theory and you're talking about games, and maybe if you're going to do a project, you might describe a game in your project, and it's important to always very clearly define the following 3 things. Okay? Firstly, there's always a set of players. You have to specify precisely who the players of your game are. These players can all take a range of actions. Okay, so here the actions are just cooperate or defect. Okay, in the games we'll be looking at later, Bertrand and Cournot competition, the actions will be the price you set or the quantity you set. Okay, and then you have to specify some payoff for taking those actions. So here it's these utilities, which are 3 minus the number of years you end up in prison. Okay, so let's play this game. Okay, so I want everyone to close their eyes. Okay, close your eyes. Go on. Okay, now put your hand up if you'd like to cooperate. Okay, that's everyone. Put your hand up if you'd like to defect. Okay, okay. So we had 8 people cooperating. So you're quite a nice bunch. And then 30 or so defecting. So, you know, what's the equilibrium of this game? I guess you've seen it before. You defect, okay? So you know, you nice people who were cooperating, if you'd been matched against one of those bastards who was over there, you would have been going to prison for a long time. Okay, so let's just remind ourselves why the equilibrium is to defect, not to cooperate. Okay, so suppose that player A knew that player B was going to cooperate. Okay, so prisoner B is cooperating. Okay, so prisoner A can either cooperate and get a utility of 2, go to prison for 1 year, or he can defect and get a utility of 3, not go to prison at all. Okay, so given a choice between 2 and 3, he prefers 3. Okay, so if prisoner A knew that prisoner B was going to cooperate, prisoner A would want to defect. What about if prisoner A knew that prisoner B was going to defect? Well, if prisoner B is defecting and prisoner A cooperates, then A is going to prison for 3 years. He gets a utility of 0. Okay, so he doesn't like that. And if prisoner B defects and prisoner A chooses to defect as well, then they both go to prison for 2 years, they get a utility of 1. Okay, so he prefers, in this case, to defect rather than cooperate as well. So it doesn't matter whether the other guy cooperates or the other guy defects. In either case, this guy prefers to defect. Okay? In either case, you know, 3 is bigger than 2, 1 is bigger than 0. Okay? So we say that defect is a strictly dominant strategy. It doesn't matter what the other person does, you always prefer to choose defect. Even if you knew what the other person was going to do, you'd always choose to play defect. Okay, so that means defect is a dominant strategy of this game. So we call this defect. We call it an equilibrium in strictly dominant strategies. Okay. So defect is the dominant strategy, cooperate is the dominated strategy. Okay, with 2 different things. Okay, so that's a game you've seen before. This one maybe you haven't seen before. It's called Stag Hunt. I don't know who comes up with these games. This one's even sillier than the last one. So we're two hunters, and they're in the forest. They're lying in wait for a stag. Okay, they want to shoot a stag. Okay, they're hiding behind a bush, and they know sooner or later the stag is going to run across their path. Okay, but they're hungry. Okay, they want to eat something, so they quite like to eat venison when they shoot the stag. But if a hare runs past, then they'll be quite tempted to shoot the hare and eat some hare instead. Okay. But the problem is, if they jump out, if they shoot the hare, they make a noise, they jump out to get this hare, that's going to scare the deer away, and they're never going to be able to shoot the deer. Okay, so they've got a choice between lying in wait and hoping that this stag comes past, okay, or jumping out and getting these hares when they come past. Okay, if one person jumps out to get a hare, then the deer's scared away, so the person who stayed behind, he's not going to end up with anything at all. Okay? If they both jump out to get hares, they both get hares. But if they're both patient and stay quiet behind their bush, eventually the stag is going to come past and they're going to get to eat stag for dinner. Okay? So this is how we represent it in a matrix. Okay, so the two players have two different options. So one is to wait patiently for this stag to come. The other is to catch the hare when the hare arrives. Okay, so hares have run across. You've got a choice of like jumping out and grabbing a hare, or just waiting patiently for a stag to come. So if they both wait patiently for a stag to come, they both get a utility of 2 because they really like eating stag meat. Okay. If this guy waits patiently, but the other guy jumps out to catch the hare, then the stag is frightened away. Okay, the guy who was waiting patiently gets nothing, but the guy who's jumped out to get the hare gets to eat some hare meat, and that gives him a utility of 1, which is less than the utility of eating stag. Okay, this cell here is just the opposite. So this is hunter A jumping out to catch the hare, and hunter B waiting patiently. And here we have the case when both players jump out to catch a hare. Okay, so let's do the same thing with this game. Everyone close their eyes. Okay, put your hand up if you'd like to wait patiently for the stag to come. Just counting, give me a second. Okay, and hand up if you'd like to jump out and catch a hare. Okay, good. Okay, so that time it was about 18 for waiting for the stag and 16 for jumping out for the hare. So you were quite evenly balanced there. So you clearly realise that this is a different game to the Prisoner's Dilemma. That there's something different about this game. But all that's changed is that here we had 3s. Okay, 3s in the corner, and now we have 1s in the corner. Otherwise the game is exactly the same, all the payoffs are the same. So, do you think there's a dominant strategy in this game? No. No, because if you knew, suppose Hunter A knew that Hunter B was going to play stag, okay? So you're definitely in this column, okay? Then in that case, Hunter A would prefer to play stag as well, wait patiently. But if Hunter A knew that Hunter B was going to play hare, okay, then Hunter A is kind of choosing between this and this, okay, so Hunter A would prefer to play hare as well. So if you knew the other guy was going to wait patiently, you'd like to wait patiently. If you knew the other guy was going to jump out, you'd like to jump out.
But would they ever choose to jump out because they get high utility from waiting?
Well, if you believe that the other person was going to jump out for some reason, then wouldn't you jump out?
Yeah, but you'd know that they'd get a high utility from waiting.
Okay, so yeah, there's another argument there. You just don't know, right? If maybe they think that you're really impatient, okay? So or maybe you think that they think you're really impatient. You know, you can do this as many times as you want, okay? And the further you push it back, the more plausible it starts to look. You know, if you're a little bit worried that the other person's going to jump out, then you're going to be tempted to jump out. Okay, even if you just got a tiny worry about the other person jumping out, you might want to jump out yourself. Okay, so it turns out that there are actually at least 2 equilibria in this game, and then we're going to see that there's actually a third equilibria as well. Equilibrium. So you've seen this definition before. Okay, an outcome is called a Nash equilibrium if, given how everyone else is behaving, each player is behaving optimally. Okay, so you know I'm one of these players. Imagine that I somehow knew what you were going to do. Okay, as long as I'm choosing what's optimal for me, given what you're doing, that's a Nash equilibrium. Okay, so if I knew that you were playing stag, then me playing stag would be a Nash equilibrium. Likewise, if I knew would be my optimal choice. So if I knew you were playing hare, then me playing hare would be a Nash equilibrium. An optimal choice. I'll say that again. If I knew you were going to play stag, okay, then it's optimal for me to choose to play stag rather than hare. Okay, so playing stag is my optimal choice, given that you're playing stag. Likewise, if you're playing hare, then me playing hare is my optimal choice. Okay, and because this game is symmetric, this means that stag and hare are the 2 Nash equilibria of this game. Okay? You know, so each person is behaving optimally given how the other person is behaving. Okay, so now, so those are 2 equilibria. Turns out that these nice games in a matrix, they always have odd numbers of equilibria. Okay, and I don't know, have you seen the film A Beautiful Mind? Yeah? Okay, so John Nash, who Nash equilibrium is named after, okay, he proved this theorem that these games always have an odd number of equilibria, you know, amongst defining what these equilibria are as well. Okay, so let's see what this third equilibrium is, which maybe you haven't seen before. Okay, so maybe suppose that both of these hunters have a coin in their pocket. Okay, and they can secretly flip the coin without the other one seeing. Okay, and what they're going to do is they're going to toss the coin, and if the coin comes up heads, they're going to wait patiently for the stag, and if the coin comes up tails, they're going to jump out and catch the hare. Okay, it seems like a slightly strange thing to do, but it's going to turn out it's an equilibrium. Okay, so imagine you thought the other person was going to do that. Okay, would you prefer to play stag or to play hare? Hare? Okay, well, why would you prefer to play hare?
Because you're guaranteed utility.
Yeah, well that's true, but if you played stag, you know, you've got a chance of getting a really big utility. So
but if they get the coin and tails, then you get no utility, whereas if you always decide to play hare and if they've got a stag or hare, you get a utility.
Once the rest are working.
Pardon?
It's guaranteed.
Yeah, so you know, if these were kind of monetary values and you were risk averse, then that would make sense. Okay, but these are supposed to represent utility. Okay, so there's all of the risk aversion of these 2 players is already encapsulated in these numbers. Okay, if they're really risk averse, then you know, this number would be smaller maybe. Okay. Have you got your hand up? No. No. Okay.
Sorry, is anyone listening?
There must be some somewhere. Okay, well, so the thing to do is to work out the 2 players' expected utility in both cases. Okay, so suppose I'm player Hunter A and I think Hunter B is doing this thing, flipping the coin. Okay, if I play stag, then I've got a 50% chance of getting a 2 and a 50% chance of getting a 0. So what's my expected utility? 1. Okay. If I play hare, then what's my expected utility? 1. Okay, so it's 1 in either case. So it doesn't matter if I play stag or hare, my expected utility is the same. You know, it happens, but it's risky in one, but not in the other. But kind of all my risk aversion is already encapsulated in these numbers, if you like. Or you can imagine that this is such a small number that I'm no longer risk averse anymore. So I'm going to be indifferent between playing stag and playing hare. Given the other person is tossing the coin, it doesn't make any difference to me whether I play stag or hare. Okay, and because I'm indifferent, I might as well toss a coin as well. I don't lose anything from tossing a coin. So, given one person is tossing a coin to choose what to do, then you know it's perfectly compatible with optimal behaviour for the other person to do the same thing. Okay, so this coin tossing is the third equilibrium of this game. It's what we call a mixed strategy equilibrium. Both players are randomising over the two options. Have you seen mixed strategy? Okay, you've seen this before. Maybe I think they're teaching progressively harder things as the years go on. People last year hadn't seen these equilibrium. Okay, well if you've seen mixed strategy equilibrium before, it's not going to be hard for you to answer this question at the bottom. If I replace the 2's by 3's above, what would the new equilibrium look like?
We play stag. You get utility 1.5.
If you thought the other person was just tossing a coin like that and it was 50-50, then that would be the sensible thing to do. But would the equilibrium have someone just tossing a coin? What if you gave both players a dice to roll? So if they had a dice to roll, how would you construct this equilibrium? So maybe it doesn't need to be 50-50. You got an idea? No? So the key thing in the last example was that given what player B was doing, player A was indifferent. Okay, so the way you solve these mixed strategy games is to choose the probabilities to make the other person indifferent. Okay, so if these were 3's, how would we make the player indifferent between stag and hare? Okay, in the hare case, they get a utility of 1 in either case. So what must the probability of stag be for them for this to give them a utility of 1? So this is a 3 now. What's another?
Just a third.
Yeah, exactly. So if there's a probability of a third, but the other person's going to play stag, then you're again going to be indifferent between stag and hare. Okay, so it's like what both players, if these were 3's, what both players would do is they'd roll a dice, okay, and if the dice was 1 or 2, they'd play stag, otherwise they'd play hare. And again, that's an equilibrium for this game. Okay, so these mixed strategy equilibria are a bit strange, but you know they're perfectly valid equilibria of these games, and you know you do see them in real life as well. You know, if you like, the fact that roughly half of you wanted to play stag and roughly half of you wanted to play hare is almost evidence of you playing a mixed strategy equilibrium, right? You know, it's like before putting out your hand, you kind of randomised whether you're going to play stag or hare. And if I randomly match 2 of you together, you know, there's a 50-50 chance each of you would play stag or hare. Okay. So they're not so strange, these mixed strategy equilibrium, okay? And what we're going to see later is that Bertrand competition that you've seen 1,000 times actually has mixed strategy equilibria as well as the normal ones. Okay, so Bertrand is going to be a lot stranger than you thought it was. Okay, so here is Bertrand. Okay, I'll do the general setup first, then we'll do a specific example, and then we'll kind of do the general properties, okay? I'll go quickly, as I guess you've seen this before. Okay. So for n firms producing an identical product, Firm 1 is constant marginal cost C1, firm 2 is constant marginal cost C2, etc., etc. Okay? So they can all have different marginal costs potentially. We're going to call firm 1's price P1, and we're going to call firm 2's price P2, etc. Firm 3, P3, etc. And in order to make our life easier, we're going to assume that price has to be discrete. Okay, so all prices have to be specified as a multiple of some small amount. So, you know, it's like all prices have to be specified in pounds and pence. You can't have anything less than a penny. You can't set a price of 1.5p. Okay? And this is just going to make our life easier if all prices are always set in discrete amounts. So we're going to call the minimum amount epsilon, this symbol here. Okay, so you can think of epsilon as being 1 penny or 1 pound or something. There's going to be some demand curve for the product, Q of P. And consumers will always buy from the cheapest firm, as you'd expect. If several firms are selling the same price, then the consumers are going to be evenly split between those firms that are selling at the same price. Okay, it's important to specify what happens in this case because that will have an impact on the equilibrium. And we're going to define the price that consumers pay as P star, okay, which is just going to be the minimum of all the prices set by firms. Okay, so the market price P star will just be the minimum of each of the firm's prices. Okay. So that's the general setup. So let's have an example. We have 2 car firms, they're competing in price, and they have to price in whole pounds. You know, you never see an advert for a car that's £2,000 and 12 pence. It would just be crazy, right? Okay, so prices have to be in whole numbers of pounds. And we're supposing that firm 1 has marginal cost of 4,000, firm 2 has marginal cost of 6,000. So maybe this is Toyota and this is Ford. Okay. And we're going to have a demand curve for the product, which is just linear, 5,000 minus P. Okay, so the first question is, what price would firm 1 set if firm 2 wasn't around? So that's just a kind of standard monopoly problem. Can you solve that? Yeah? 500. Does everyone agree that it's 500? That seems slightly surprising. Well, the marginal cost is, so firm 1's marginal cost is 4,000, so they're probably not going to price less than 4,000. Have you missed a 0 maybe? Any other offers? So once you've done this, I'll show you a trick for solving these problems incredibly quickly. With linear demand, you really don't need to differentiate anything. But have you got that? You've got a 4,500. Okay, that sounds more plausible. Maybe that's what you meant before. Okay, so let's have a look. Thank you. So you know, first thing we do is always write down profits. Okay, profits are here we know it's kind of constant marginal cost of 4,000. Okay, so it's quantity times price minus marginal cost. Okay, it's constant marginal cost, so that's QC is your total cost. Okay, so substituting in, this is 5,000 minus P times P minus C, which was 4,000. Okay. Okay, and without doing anything else, without differentiating, I can tell you that that's maximised at 4,500. Okay, and the reason you can just jump to that is because this is a quadratic, right? Okay, you know that one of the roots of the quadratic is at 5,000, one of the roots of the quadratic is at 4,000. So by that I mean when P is 5,000, this is 0. When P is 4,000, this is 0. And if you remember what the graph of the quadratic looks like, it's like this. Okay, here's one root, here's the other root, and the maximum is always halfway between the two roots. It's just a nice property of quadratics. Okay, so you don't need to do any differentiation here. You see the two roots straight away, and so you know the maximum is halfway in between at 4,500. Can everyone see that as well? Okay, so that's fairly straightforward. So that's the monopoly problem. Normally when you solve Bertrand problems, you kind of ignore the demand curve completely. We'll see, but it's important to remember that the demand curve is there in the background. Okay? So the next question I've got here is, what's the maximum difference between the price set by both firms in any Nash equilibrium? Okay, so imagine an equilibrium. How big a difference can there be between the price of one firm and the price of the other firm? So could there be a difference of £10 ever? So imagine one firm was pricing at £7,010, the other firm was pricing at £7,000. Would the firm pricing at £7,000 like to deviate? Someone's shaking their head, someone's nodding. What would they like to deviate to? Yeah, exactly. They'd like to go up to 7,009, right? You always want to be charging as high a price as you can, subject to being the cheapest in the market. Okay, so there's never going to be a difference of more than £1 between the two prices. Otherwise, the guy at the bottom would like to increase his price. Okay, so you know that at most the difference between the two prices is £1. Okay, now I say in the Nash equilibrium in which firm 1 is making the highest possible profits, so this is suggesting that there might be more than one equilibrium for this game already, but what prices does each firm set? Okay, so for firm 1 to be making as high a profits as possible, what price do you think he's going to be selling? So, imagine that firm 1 sets a price of £5,000. Is that likely to be an equilibrium?
No, because sorry, I read it.
Okay, or even higher. Okay, imagine firm 1 sets a price of £7,000. So if firm 1 was setting a price of £7,000, what would firm 2 like to do?
Set a price lower than that?
Yeah, a bit lower. So firm 2's marginal cost is 6,000. So firm 2 would happily go to 6,999 certainly. And you can think of them, pushing the price down. So now imagine firm 2 was setting a price of £6,001. Could that be an equilibrium? No? Someone says, why not?
Firm 1 just goes to 59999 and put them out of business. Well, not put them out of business, but they move loss.
Okay, well, so if firm 1 is at 6001, firm 2 is at 6001, firm 1 can even go to 6000. You know, they don't have to go to 5999. And so it's a possible equilibrium, right? Firm 1 at 6000, firm 2 at 6001. Would anyone like to deviate from that? That's the question. So firm 1 is the only one who's selling, right? He's got the cheapest price. Firm 2, would firm 2 like to deviate? Yeah, he could reduce his price to 6,000, but at 6,000 price is equal to marginal cost, so he's not making any money. So he's kind of indifferent between setting a price of 6,001 and 6,000. So there's going to be an equilibrium here in which firm 2 sets a price of 6,001, firm 1 sets a price of 6,000. Okay, so that's going to be the equilibrium in which firm 1's making the highest marginal cost, highest profits. Nonsense. Are there going to be any other equilibria? So what if firm 2 set a price of 5,500? Could there be an equilibrium in which firm 2 was selling a price of 5,500? Given what we said here, what price must firm 1 be setting? 1 less, yeah. So firm 1 was setting a price of 5,499, and firm 2 was setting a price of 5,500. Again, yeah, firm 1 is the only one who's selling anything. Firm 1 wouldn't like to cut his price because then he loses profits. If he increases his price, he then has to share with the other guy, so he wouldn't like to do that either. The other guy is pricing below marginal cost, which seems a bit weird, but he's not actually selling anything, so he doesn't care about pricing below marginal cost. Okay, so there are other equilibria here in which this guy actually prices below marginal cost, but because he's not selling anything, all he's doing is stopping the other guy from selling a too high a price. Okay, so these Bertrand games generally have lots and lots of equilibria. So in fact, any price between 4,000 and 6,000 is going to be an equilibrium of this game. Okay, so so that was an example to show you the kind of problems we have in solving these Bertrand games. Now let's see things a bit more generally, and I'll just take you through two little mini theorems which will show you how to solve these games for any game. So we go back to this framework where we have n firms and they're indexed by I. I is 1 to n. Okay? So what we said is, imagine, just for the sake of argument, that there is some firm I such that firm I was setting a price above the market price, P star, so above the lowest of all the prices, and P star was bigger than firm I's marginal cost plus epsilon, where epsilon is this increment. Okay, so if firm I is above the market price, they're not currently selling anything, but P star is bigger or equal to firm I's marginal cost plus a penny or something. So if firm I switched to setting a price of this, Ci plus epsilon, they would then be the cheapest firm, and because they're setting a price higher than their marginal cost, they're making profits on every unit they sell as well. Okay, so if it was ever the case that this was true, then firm I would like to deviate to setting this price. Okay, so in any equilibrium, it can't be true that this is the case. In any equilibrium, in any pure equilibrium at least, and for any firm I, if the market price is bigger or equal to firm I's marginal cost plus epsilon, then firm I must be at the market price. Okay. So this is kind of a little result about undercutting. All that's going on here is they're undercutting. if you see that the market price is higher than your marginal cost, then you want to go in at a price between the market price and your marginal cost. Okay, that's all this is saying. And we've got another result for the case when two firms are selling the same price. Okay, so imagine that both firm I and firm J are selling this price of P squared. And imagine further that P star was bigger than Ci plus epsilon. Okay, so firm I was pricing quite a bit above their marginal cost. So at the moment the demand is split between these two firms, right? We said if two firms were pricing at the same amount, then they both get half of the demand. But this guy is pricing quite a bit, a little bit above his marginal cost. So again, he'd like to undercut. Okay, and what he's going to do, he's going to set a price of, just epsilon less from the price he was setting before. Okay? So if he was setting pi before, he's now going to want to set a price of pi minus epsilon. Okay, so he's just taking a pound off his price. And by doing this, he's then the cheapest price in the market. So rather than sharing the demand between I and J, well, now all of the demand is going to I. However, he's cut his price a bit. So there are two effects here, right? He's reduced his price, but the quantity's increased. So which dominates is going to depend on how small this reduction in the price was. But at least if epsilon is very small, then he's hardly reduced his price at all. Okay, so the increase in demand is going to dominate the reduction in the price. Okay, so for small epsilon, these firms would always like to undercut, okay, to ensure that they get the whole market. Okay, so we have this general result for Bertrand competition, but for small enough epsilon, in any pure equilibrium, there can be at most one firm who's selling a price that's above their marginal cost plus a penny. Okay? So there can only really be one firm in Bertrand competition who's making a proper profit. Okay, there might be some firms who are pricing at epsilon above their marginal cost, but only one firm can be making a profit bigger than epsilon on each unit sold. Okay. As epsilon gets smaller and smaller, this is just saying that in Bertrand competition, only one firm can make a profit. Okay, so if we go back to this car example, we saw that the only guy who made a real profit was the guy with the lower marginal cost. Yeah.
Well, they have the same marginal cost.
So if they have the same marginal cost, we can use these theorems. Okay, so we know that there's not going to be anyone setting a price. Let's go to the next slide. It's on the next slide. Okay. So if Ci is C for all firms, so everyone has the same marginal cost. Okay, then by what we just saw was at most one guy who's setting a price that's strictly above his marginal cost plus a penny. Okay, but everything's symmetric, so there's not going to be one guy. There's going to be exactly 0 guys. And as long as there are more than 2 firms, no one is going to be setting a price above this amount. Okay, just imagine that there were 2 firms and one of them was setting a price above Ci plus epsilon. Okay, then the other one would like to undercut and set a price of Ci plus epsilon. So with symmetric marginal cost, price gets driven down almost to marginal cost. Okay, with epsilon small, price gets arbitrarily close to marginal cost. As long as there's more than one firm in the market. But if n is 1, then this is just a monopoly problem. Right? So that's what I'm saying now. So as long as there are at least 2 firms, then the market price is between marginal cost and marginal cost plus an epsilon. Okay, so the equilibrium when marginal costs are the same are going to be both firms pricing at C plus epsilon and both firms pricing at C. Okay, if both firms price at C plus epsilon, then if anyone undercuts, they have to undercut to their marginal cost. And if they do that, they don't make any profits anyway, so they don't benefit from that undercutting. Okay? So that's going to be an equilibrium. If both firms price at marginal cost, they're not making any profits. They certainly don't want to price even lower because then they're making negative profits. If they price higher, they no longer sell anything, so they still make no profits. Okay? So generally when everyone has the same marginal cost, we're going to be two equilibrium. One with everyone pricing at marginal cost, one with everyone pricing 1 penny above marginal cost. Okay. So what you normally see is results for very small epsilon. So when epsilon goes to 0, price is equal to marginal cost, basically. But it's a bit hard to define the game when price can take a continuum of values. Okay, before we do this slide, let's just go back to this one. Okay, because there was something I forgot to mention, right? Remember, we showed in this example that the monopoly price was 4,500. Okay, so I should have remembered this earlier. Firm 1 never wants to price above the monopoly price. You know, once above the monopoly price, marginal revenue is going down, right? It's negative even. Okay, so firm 1 never wants to price above 4,500. So the maximum profit equilibrium here is firm 1 pricing at 4,500, and it doesn't really matter what price firm 2 sets. As long as it's above 4,500, because firm 1 doesn't want to increase their price. Okay, so you know, the easiest way to solve these games is to solve first, just as we did, solve first ignoring the demand curve, ignoring what the monopoly price is, and then once you solve them, think about which of those equilibria are ruled out because of the monopoly price. Okay, and that's what we're going to do when we see the set of equilibria in the general specification of the game. Okay? So we've got two cases. Okay, in the first case, for at least two firms that have the same marginal cost, and we don't know what the other firms have, what the marginal cost of the other firms is. In the other case, everyone has different marginal costs. So in the first case, when at least two firms have the same marginal cost, equal to the minimum, okay, then those two firms are going to compete the price down, just as you've seen before, to either this minimum or this minimum plus epsilon. Okay, so we get a kind of competitive solution. But if there's only one firm that has the minimum marginal cost, okay, then the unique firm K, whose marginal cost is equal to the minimum of the marginal cost, okay, then that firm is going to set a price somewhere between CK plus epsilon, so 1 penny above that marginal cost. That's the lowest we're ever going to be prepared to go. And the highest they're ever going to be prepared to go is the monopoly price, PM. Okay, they never want to price above the monopoly price. But they also have to price weekly below the next highest marginal cost. Okay, so just as we saw in this example, you know, you can't have firm 1 pricing at 6,001 because then firm 2 will undercut. Okay. So they're going to set a price somewhere between 1 penny plus their marginal cost and the minimum of the next highest marginal cost and the monopoly price. Okay, and it's going to turn out that any price in that interval will be in equilibrium in this game. And basically, it's supported, just as we saw before, you know, the guy with the next highest marginal cost is going to set a price that's epsilon above the price of the guy with the lowest marginal cost. And even though the guy with the second highest marginal cost is pricing below his marginal cost, because he's not selling anything, he doesn't care about that. Okay? So Bertrand competition has this continuum of equilibrium in that interval. Okay? But when I ask you a question, I'll often ask for a particular equilibrium, and the one I'll often ask for is the one with maximum profits. Okay, this is the kind of a natural equilibrium of the game. So just as you thought earlier that that stag was the natural equilibrium of stag hunt, okay, because stag was the one in which everyone is better off. Here we're going to concentrate on this natural equilibrium in which profits are highest, okay, and the one in which profits are highest is the one in which this firm K is setting price equal to this. Okay, so the guy with the lowest marginal cost is going to set a price equal to the minimum of the second highest marginal cost of a monopoly price. He can't go above the second highest marginal cost because then he'll get undercut, and he doesn't want to go above the monopoly price. Okay, we better have a short break, but not too long because we're a bit late starting. Okay. So why don't you just shout out the answer as we go through. So the question is, in each case, which firms sell and at what prices? So we haven't specified the demand curve. You can just assume that demand is completely inelastic. Okay, so it doesn't matter what price they set, they're always going to sell the same quantity. Okay, and they're pricing in whole pounds, and there are 3 firms. Okay, so the first example, that's the same marginal cost. What are the 2 equilibria? Yeah, 100 and 101. Yeah, exactly. So if everyone's pricing at 100, no one's making any profits. If they increase their price, well, they still don't make any profits. So pricing at 100 is an equilibrium. At 101, everyone's making £1 profit per unit sold. But if they cut their price to 100, then they're not making any profit anymore. Okay, so they don't want to undercut at that point. So 100 and 101 are equilibria here. In this next example, C3's marginal cost is now 200. What are the equilibria?
Anything between 100.
Pardon?
Is it anything between 100 and 200?
Well, there are 2 firms with marginal costs of 100. So maybe that changes things.
133.
Lots of answers? It's the same. Okay, that's right. Okay, so, you know, it kind of doesn't matter what this third guy's doing at the moment, because you've got 2 guys with the same marginal cost, so those 2 kind of compete the price down, if you like. You know, if the price was 200, one of these guys would want to set 199. And then the other one would want to set 198, etc., etc. Okay, so again, it's 100 or 101 here. But now in this case, there's only 1 firm with marginal cost of 100 and 2 firms with marginal cost of 200. So now what are the equilibria? This is more like what you thought it was last time. 200 and 201.
And between 100 and 200. But then firm 1 can
Okay. I've heard the right answer a few times. So anywhere between 100 and 200 is an equilibrium. Okay. No, it can't be 200. So anywhere between 100 and 199. Okay. At a price of 200, they have to share their demand between the 3 of them. Oh, no, sorry, I'm wrong. Yeah, anywhere between 100 and 200, you're right to start with, because at 200, you can have an equilibrium in which he prices at 200, he prices at 201, he prices at 201. Okay, no one wants to deviate there. Yeah, they're not selling, they don't really care. If they reduce their price, they don't make any profits.
Why would C1 go to 200 or 201? I'll just stay.
Because if C1 goes to 201, then he then has to share demand with C2 and C3, with firm 2 and 3. Okay? So as long as demand is big enough, they never want to share demand. Okay, so anywhere between 100 and 200 would be an equilibrium. You can see why 100 is an equilibrium. That requires him setting a price of 100, him setting a price of 101, and we don't care what price he sets. Okay, it's slightly strange because this guy has a marginal cost of 200, he's setting a price of 101. But given the market price is 100, the guy setting a price of 101 isn't selling anything. So he doesn't care about pricing below marginal cost because he knows he's not going to have to sell anything below marginal cost. So it's like, you know, they're advertising that they've got this good price, but they know no one's going to take it because someone else is selling it cheaper. So it's slightly strange, but you know, it's still an equilibrium. So you can think of it as like the hair equilibrium in stag hunt, okay? You know, you thought it was quite strange that these people would ever go to this hair equilibrium. But you know, as far as the definition of Nash equilibrium is concerned, it's a valid equilibrium. Okay, the next one is getting a bit more complicated. 100, 102 and 104. Yeah, so I think it should be the same as this. So let's assume it's anywhere between 100 and 102. That would be the obvious thing. So if it's a price of 100, he sets a price of 101, and then everything's fine. Okay, if he sets a price of 101, he sets a price of 102. That's fine. He sets a price of 102. He has to set a price of 103. And he has to set a price, yeah, he can set a price of 104, so that's an equilibrium. Okay, so anywhere between 100 and 102 here. And then in the final one, what's the equilibrium?
Wait, no, what? 100 and 102?
Anywhere between 100 and 102, yeah. Just like this one was anywhere between 100 and 200. So it didn't actually really change anything. But this third one, that might be a bit different. Maybe it's not. Yeah, that would be the sensible guess, wouldn't it? So 100 certainly is. He sets the price of 100, he sets the price of 101, so does he. Is 101 an equilibrium? Well, he has to set a price of 101. If he set a price of 101, you know, he wouldn't be making any profit. So, you know, he's happy to set a price of 102, so that's fine as well. So 101, 102, 102 would give you the other equilibrium. So it doesn't really make a difference. In any case, it's, you know, the interval between the lowest and the second lowest.
Well, what's the last equilibrium?
So anywhere between 100 and 101.
Just a question, between the second and the third one, why, like, for, yeah, the third one, why can't firm 1 match his price at firm 2 and firm 3's marginal cost and make a profit, rather than stay at 100?
He can. So anywhere between 100 and 200 is an equilibrium. So, you know, the sensible equilibrium here, the profit maximizing one, is the one in which firm 1 sets the price of 200. He sets the price of 201, he sets the price of 201.
And then for the second one, if they both do it the same as the third one, if they both set the price at 199,
okay,
and they both make the profit.
They both make a profit, but if he's setting a price of 199, he's setting a price of 199, then one of them would like to undercut and set a price of 198. Okay, so if you've got two firms with the lowest marginal cost, then the competition kicks in. Okay, and the price gets driven down.
So did you...
I don't understand why firm 3 with like 104 and 102 aren't in the equilibrium. I would say it would be between 100 and 104.
100 and 100 in this case?
Yeah.
So say it was 104, then this guy would like to undercut to 103. Okay, because his marginal cost is 102, so he can undercut as far as 103. And then, you know, if it was 103, then he would happily undercut to 102. Okay, so but if it's 102, then you know, if it's 102, then this guy's not making any profit on each unit he sells. Okay, so you can put him at a price of 103 if he's indifferent. Okay, so him at a price of 102, this one at a price of 103, this one doesn't really matter, 110, who cares? Okay, that's going to be an equilibrium.
You just say it's always the price between the lowest and the second lowest or highest.
Yeah, so in these cases when there's a unique firm with the lowest price, okay, the price is anywhere between the lowest and the second lowest.
Second lowest.
Yeah. Okay, so anywhere between 100 and 101 here, 100 and 102 here, 100 and 200 here. You know, these examples are all really the same. Okay. Yeah, I say how the demand curve might affect your answers. Okay, when I tell you the demand curve, you know, you've got to work out the monopoly price, and in each case you've got to make sure that the guy with the lowest marginal cost doesn't end up pricing above the monopoly price, because he never wants to price above the monopoly price. Okay, so this was virgin competition. You've seen virgin competition before, but you know, maybe you now think it's slightly more complicated than you saw it before. But it's you know, it's the same fundamental idea as what you saw in previous years. You just have to think about the competition that's going on. So we've seen all the pure equilibria of virgin competition, and there were lots of them. I'm now going to show you one of the mixed equilibria of virgin competition. Okay, which is going to be very different. So we're going to suppose that there are two firms. They both have the same marginal cost. Okay, we'll set the marginal cost to 0 to make our life easier. Okay, so C1, C2 is 0. And consumers have inelastic demand. It doesn't matter what the price is, they always want one of the unit. Okay, so you know, we have inelastic demand for water. If these are two water companies, it doesn't matter what the price is. If I don't have water, I'm going to die. So, you know, I'm going to pay any price you can charge me to get some water. Okay. So there are some goods for which inelastic demand is reasonable. Okay. So with inelastic demand, monopoly profits are going to be infinite. You know, you can set a price. It doesn't matter how high you set your price. Demand is always 1. I set a price of £100,000 per bottle of Evian. You're going to buy it if you really need a drink of water, otherwise you'll die. All this drink of water, it's making me thirsty. Okay. But if it was virgin competition here, you know, profits are basically 0. Okay, with the two firms having the same marginal cost, profits of the marginal cost plus a penny. Okay, so with normal, pure virgin competition, the profits would be 0. Okay, so we've got infinite profits under monopoly, profits of 0 under pure virgin competition. Okay, and what we're going to see is that mixed strategy virgin competition is going to get you somewhere in between. So let's just fix some number z. Okay, it doesn't matter what z is, any number will do. Okay, any positive number. So z is just some large number. And let's suppose that each firm never chooses a price less than z. Okay, and for any price p bigger than z, each firm decides to choose a price greater than p with probability z over p. Okay, so this is giving the cumulative distribution function the firm's choice of price. Okay, you've seen, you know what a cumulative distribution function is? Cumulative distribution function. No, didn't you do this in stats? In econometrics, surely. So, could you point that to? Okay, if I showed you this graph, what would you say it was? Okay, that's the probability density function of the normal distribution. Okay, the indefinite integral of a probability density function is the cumulative distribution function. Okay, so for the normal it looks like that. You haven't seen graphs like that before? Yeah? Okay. Now, so this graph gives you take a point here, this height is the probability that you get a draw to the left of that point. Okay, so the height of the CDF gives you the area of all of this. So it's the probability of getting a draw to the left of that. Okay, what we're going to do is we're going to choose a cumulative distribution function for the way these firms are going to randomize over their price. Okay? And I'll draw the cumulative distribution function we're using, so you can see how it'll be. Okay, so I say for any price P with P greater than Z, okay, so here's price, here's probability. Okay, this is going to go from 0 to 1. Probability. So firms never choose a price less than Z, I say. So the probability of choosing a price less than Z is 0. Okay, so the cumulative distribution function is 0 up to this point Z. For any point price P bigger than Z, each firm chooses a price greater than P with probability Z divided by P. Okay, so just think what that looks like. As P goes to infinity, Z divided by P goes to 0. Okay, so the probability of choosing a price bigger than that is going to 0. So the higher the price is, the less likely it is to choose. You know, this is Z over P looks like that. Okay, that's giving us the probability of choosing a price bigger than P. So the probability of choosing a price less than P, which is what the cumulative distribution function is going to be 1 minus Z over P. Okay, so it's going to look like that. So this is the cumulative distribution function firms are using to randomly choose their price. Okay, so you know you could draw the density function for this distribution as well if you wanted, but you can kind of see how it works. You know, here's a probability of a half. Okay, so there's a 50% chance that they're going to choose a price in this interval. Okay, so maybe here's a probability of 90%. So there's a 90% chance we're going to choose an interval, a price in this interval. Okay, so they're probably going to choose quite a low price, but there's at least some probability that they might choose a very high price. Okay. And just as when we looked at the mixed strategies of the stag hunt game, we had to show that given the other person was randomizing, you were indifferent. That's what we're going to do here as well. Okay, so suppose that firm 1 knows firm 2 is picking their price at random using this probability cumulative distribution function. So given this, what's firm 1's profit from choosing a price of P1? Okay, so firm 1 chooses the price of P1, and firm 1 knows that firm 2 is randomizing. Okay, so their expected profits are price times quantity, price times expected quantity, because this is random. Consumers only demand 1 unit of this good. Okay, so the expected quantity they sell is just the probability that they have the cheapest price. Okay, both firms are choosing price at random. If firm 1 has the cheapest price, firm 1 is going to sell the good. Okay, so the expected quantity for firm 1 is just the probability that firm 2 has a price bigger than firm 1. Okay, if firm 2 has a price bigger than firm 1 sells 1 unit, otherwise firm 1 sells no units. Okay, so the expected profits are given by this expression, price times the expected quantity. But we're told, okay, that the probability of getting a draw bigger than some constant P is given by Z over P. Okay, this was how we specified that firms were randomizing. Okay, so given what we know about how firm 2 is randomizing, we know that the probability that P2 is bigger than P1 is just Z over P1. Okay, so the expected profits of firm 1 are P1 times Z over P1, which is just Z. Okay, so it doesn't matter what price firm 1 chooses, they always make a profit of Z. So given firm 2 is randomizing in this way, firm 1 is indifferent about what price to set. Okay, so given firm 1 is indifferent about what price to set, they might as well randomize as well. You know, they might as well roll this strange dice which generates prices from that distribution. So this gives us the mixed strategy equilibrium of Bertrand competition. Okay, these firms are going to price at random and you know, they're prepared to price at random because they know the other person is pricing at random as well, so they end up being indifferent about what price they set. Okay, and this might seem completely crazy, but you know, if you think about firms that set prices quite quickly, so they can't respond to price cuts from other firms, then this might be a reasonable model. You know, if you think about sales at supermarkets often have these sales that are very quick, you know, they only last a day or something. So this might just be an example of supermarkets randomizing. Okay, they're deliberately randomizing, they're playing a mixed strategy. Okay, and you think sales are a good thing, this random element in pricing, but really it's a way of them increasing their profits. You know, we didn't say what this Z was, okay, but somehow firms ended up making a profit of Z. So we could have set Z at £1 billion, and firms would have ended up making a profit of £1 billion. Okay, so there are infinitely many mixed strategy equilibria here, and they make any profit in these mixed strategy equilibria from 0 to infinity. Okay, so with inelastic demand, Bertrand competition is just completely crazy. You know, we have this mixed strategy equilibrium in which profits are unbounded. So, you know, it's quite a restrictive assumption, inelastic demand. And, you know, it's implausible in general. Even if I'd like to pay £1 billion for a bottle of water if I was dying of thirst, I don't have £1 billion, so you know there's clearly a limit to the maximum I can ever pay for something. But there's a nice paper that shows that you get mixed strategy in Bertrand competition whenever either the monopolist profits would be infinite. Okay, so if you did the exercises from last week, remember we saw that with isoelastic demand you got something like 1 over 1 minus what they call it, beta. Times cost. Okay, price was equal to that. That was the solution of isoelastic demand. Okay, so if beta goes to 1, then the monopoly price would go to infinity. Okay, so isoelastic demand with beta equal 1 would be one case where the monopoly profits were infinite, and so this argument would go through. Or alternatively, if there is some choke point in demand, okay, so demand goes to 0 beyond some point, but firms are uncertain about exactly where demand goes to 0, then you're still going to get these mixed strategy equilibria existing. So price competition it can be quite a strange thing. You know, and if we use, earlier you suggested this way of choosing equilibria, which was always choose the one which makes everyone better off. Okay, if we apply that rule to Bertrand competition, we get these mixed strategy equilibria rather than the pure ones. Okay, so just because something's Bertrand competition, you shouldn't automatically assume that profits are going to be 0. They could be infinite, you know. And you know, although this is a slightly contrived game, we're going to see similar things happening when there are multiple periods of competition. Okay. So it's not completely crazy. Okay, in the last half hour we'll just go through Cournot again, just as a revision for future things. You've seen Cournot before, I presume? Cournot is going to be the same as what you saw before. There's nothing strange about Cournot. I think you saw everything there was about Cournot before. So there's some inverse demand curve which gives you price as a function of the quantity. We've got firms from 1 to n, Okay, firm I is going to produce a quantity Qi for the total cost function for firm I, which is giving total cost of firm I as a function of Qi, Ci of Qi. Okay, so firm I's profits are going to be given by the market price, so price is a function of total quantity, okay, which will just be the sum of all of these Qis, minus firm I's cost, firm I's total cost, Ci of Qi. Okay, total quantity is the sum over all of the Qis, that's what that's saying. Have you seen this notation before? Yeah, okay, so it's the sum from I is 1 to n of Qi. Okay, so it just means Q1 plus Q2, etc. Okay, so in the easy case when n is 2, which is maybe what you looked at before, total quantity is given by Q1 plus Q2. So, you know, the way we solve these games is we just assume that the other firm is playing the equilibrium and work out what quantity the first firm would like to set. Okay, so we're going to assume that firm 2 is playing some optimum quantity Q2 star, and we're going to work out what quantity firm 1 would like to produce, given that. Okay, so profits, as ever, are price times quantity minus cost. Okay, so price is a function of total quantity, Q1 plus Q2 star. So price times quantity minus firm 1's quantity. Okay, and then we're just going to differentiate profits to find the quantity they'd like to produce. So we've got something times something else. Okay, so we're going to use the product rule to differentiate, just like we did last week. Okay, so we get the derivative of the first thing, that's p dash, times the second thing. Okay, plus the derivative of the second thing, derivative of Q1 with respect to Q1 is just 1. Okay, so that just disappears, times the first thing. Okay, so derivative of the first thing times the second thing plus 1, which is the derivative of the second thing, times the first thing. Okay? Happy? Yeah? Minus the derivative of total costs, which just gives us marginal costs. Okay? And a maximum, the derivative of profits has to be equal to 0. Okay, so that's our first order condition. We just set it equal to 0. So that's for firm 1. We can do the same thing for firm 2. Okay, again, we assume that firm 1 is playing their optimum, some quantity Q1 star. And, you know, again, we have profits, the price times quantity minus total costs. Okay, again, we differentiate using the product rule. Okay, and we get the P dash times Q plus P minus marginal costs. Okay, so we have two first order conditions for firm 1 and firm 2 now. Okay, and the easiest way to solve these Cournot games is always to derive the first order conditions and then add them up. Okay, so even when we get to more complicated Cournot games, this is always the trick you have to use. Work out each firm's first order conditions separately and then add all of the first order conditions together. Okay, if you know, all we're doing is that if A is B and C is D, okay, then A plus C is equal to B plus D. That's the trick for solving Cournot. That's all there is to solving Cournot. So this is just like solving a monopoly problem. Now we're going to add the two equations together. So I'll do that. Okay, so what are we going to get? We're going to get... Sorry, I'm moving around. So both of these equations start with P dash times Q1 plus Q2. Okay, so this is big Q, total quantity. Okay, and then they're times, this one is times Q1, this one is times Q2. Okay, so we get P dash of Q1 plus Q2 times Q1 plus Q2. We're just adding the two equations together. Okay, and then we get P, you know, we add this and that. Okay, so we just get two copies of it. Plus 2 times P of Q1 plus Q2. Okay. minus this, minus that. Minus C1 dash, Q1 minus C2 dash, Q2. Equal to naught. There are some stars in this. Okay, the stars just denote that we're working at this is the optimum values. So all I've done is just added the two first order conditions together. Okay, and remember that Q total quantity is quantity produced by firm 1 plus the quantity produced by firm 2. Okay, so this first bit is P dashed of total quantity times total quantity plus 2 times the price at total quantity minus this thing which is marginal cost of firm 1, marginal cost of firm 2. For simplicity, we're going to put them in brackets together. Okay, so C1 dash star plus C2 dash. Okay, and then to get from this equation to the one I have on the board, on the slide, all you have to do is divide by 2. Okay, if you divide this equation by 2, you get to this equation. Okay, and then we've taken marginal cost over to the other side. So on the right-hand side, what we have is a half of the sum of marginal cost. So this is industry average marginal cost. Okay, so average marginal cost is going to be the important thing in Cournot competition. Okay, whereas Bertrand competition, it was minimum marginal cost that mattered. In Cournot, it's going to be average marginal cost that matters. Okay, and what we have on the left-hand side looks quite like the monopoly first-order condition. Okay, remember under monopoly, so if a monopolist faced this demand curve, then their total revenue would be this thing, P times Q. So marginal revenue is just P dashed Q times Q plus P of Q, using the Pareto rule. Okay, and this is almost exactly what we have on the slide here, right? The only difference is this half in the front. Okay, so going to Cournot competition, we almost get the same condition as we got under monopoly, but total cost, the marginal cost of a monopolist would be replaced by average marginal cost of the industry, and this factor of a half has entered in front of the first term of marginal revenue. Okay, and this is just because when a firm increases its quantity, okay, as a firm increases its quantity, the price it has to set decreases. Okay, if you're a monopolist, you pay all the cost of that decrease in price. You know, if you're a monopolist in a market, if you increase your quantity, then you have to reduce your price on all of the units you were currently selling. Okay, but if you're in Cournot competition and you increase your quantity, then you only have to reduce the price on the units you were selling rather than your rival. Okay, so your rival was selling half of the units before. So as you increase your quantity, the cost in terms of reducing your price, half of that cost is borne by your rival rather than you. Okay, so under Cournot competition, firms are going to have weaker incentives to keep their quantity low. Okay, so firms are generally going to produce more under Cournot competition. And we'll see this when we do the case with n firms, which is really exactly the same as what you saw here. Okay, so assuming that, so let's look at firm I, and we'll assume that all the other firms are playing their optimum quantity. Then what are profits? Well, profits are price as a function of quantity times quantity minus total cost. All I've done here is written out the total quantities as this long sum of each of the individual Qs. And again, when we differentiate this with respect to Qi, Okay, not any of the others, just qi. Here we get derivative of the first thing times the second thing. So this is p dash evaluated at this long sum, which is just q star, times the second thing, which is qi star, plus derivative of the second thing. Okay, derivative of qi with respect to qi is just 1, so that disappears, times the first thing, which was just p of q star. Okay, minus derivative of this. This is total cost. We differentiate it, we get marginal cost. So, this first order condition looks just like the first order condition you see in monopoly. It's one you'll see all the time. And again, the trick, just as with two firms, we added up the two first order conditions. Now we have n firms, 1, 2, 3, 4, 5, etc., up to n. And we're going to add up all n first order conditions. So if this is the first order condition for firm I, we can plug in I is 1, 2, 3, etc. Okay, so when we add these up, board marker. Okay, so we're adding up n copies of this from I. For I is 1 up to n. So all of them are going to start with p dash q star, and then there's going to be a sum of qi. Okay, so it's going to be q1 plus q2 up to qn. Okay, because we're adding up this. We've got n copies of this equation for each of the firms, and we're adding them all up. Sorry, this equation. Okay, and then we get p of q star. Well, that's not a function of I. Okay, there's no I in that expression, so you just get n copies of that, right? So n times p of q star. Okay, minus this last term, which is the marginal cost, and we're just going to have a sum of the marginal cost from I is 1 up to n. Ci dash. Okay, so it's just like in the two-firm case, we added up the first order conditions of those two firms. In this n-firm case, we add up the first order conditions of all n firms. And then to get to the equation in the board, I've just divided through by n. Okay, just like we did. In the two-firm case, we divided through by 2. Now we're dividing through by n. The right-hand side, just as before, you have an average of marginal cost. Okay, so the thing that matters in Cournot, again, is always average marginal cost. And what we have on the left side is just like marginal revenue from monopolist, but now we have this 1 over n term in the front. Okay, so the more firms there are, the less a firm feels the cost of increasing their quantity. Okay, so the less damage a firm does to its profits by increasing its quantity. And as n goes to infinity, what's going to happen? Pardon? Yeah, price will go to marginal cost. Okay, so as n goes to infinity, this term will go to 0. So you're just left with an expression that says price is equal to average cost, average marginal cost.
Sorry, does it become perfect competition?
Yeah, it's almost perfect competition. So under perfect competition, the price would be the minimum of the marginal cost. Okay, with Cournot competition in the limit, you get the average of all the firms' marginal costs. So if all firms have the same marginal cost, okay, then this average will just be the marginal cost. Okay, so as the number of firms increases, it will go to perfect competition. So if all firms are the same, if all firms have the same marginal cost, but as n goes to infinity, we just get price is equal to marginal cost. Okay, in this more general case, price gets closer and closer to the average of all firms' marginal costs. And I think this is about it. So here are some problems for you to do. I'll go through them in the next class. So we've got some linear demand curve and some linear cost curve for each I. And it's really very similar to the exercises you did last week. Okay, and so you show that under Cournot competition, quantity is some function of the number of firms. Okay, so you can see the difference between Cournot competition and perfect competition. The higher n is, as n goes to infinity, 1 over n will go to 0. Okay, this expression will go to the quantity under separate competition. So that's under linear demand, and then you can do the same thing under isoelastic demand. And remember, with monopoly, with isoelastic demand, we got this markup pricing, okay, where price was always 30% above marginal cost or something. Now the markup is going to be a function of the number of firms in the industry. Okay, so the more competition there is in an industry, the lower markup firms are going to be able to get away with charging. Okay, and in the limit as n goes to infinity, again, price will equal marginal cost. And the harder question is whether this is efficient or not, and we'll talk about that. And there's some more further problems in our shy, okay, and then extra further problems as well. Okay, so to conclude, so Bertrand competition, when there's symmetric marginal costs, and you only look at pure stretching equilibrium, then yes, you get efficiency. You get price basically equal to marginal cost. Okay, plus or minus an epsilon. But there's always this mixed strategy equilibrium, which can generate incredibly high prices, okay, which certainly isn't efficient. And marginal costs aren't symmetric, then Bertrand will also not be efficient. You know, price won't be the lowest of all the marginal costs, it will be the second one. Cournot competition gives you a similar expression for price and quantities to monopoly, apart from this dependence on the number of firms. Okay, as the number of firms increases, prices are going to average marginal costs. And my battery's just run out, so perfect time.